Whiteboard Physics A-Level lesson number 62, all about deformation of solids. Now, last lesson we were looking at springs and Hooke's law, and we're going to continue talking about that today. Now, we can deform solids in two different ways. We can deform solids by stretching them, which is what we were already looking at, stretching. We were looking at that with springs. So stretching, and we can look at squashing them. There are other ways of deforming solids as well. We can deform them by twisting them, and by, well, I can only think of the technical term, which is shear. I'm not sure what else you could call it. So skewing them, perhaps. Skewing might be a better way of describing it. Skewing, how do you spell skew? It's probably got a Q in it. Skewing. Or is it K? Maybe it's a K. Skewing them. So what does that look like then? We've got an object like this, and we apply two forces to stretch. And when it comes to squashing, we've got an object like this, and we apply two forces to squash it. Now with twisting, we've got an object like this, and we apply forces in such a way that the two sides twist in opposite directions. And it's difficult to represent that in two dimensions like that. Whereas with skewing, what we would be doing is having an object like this and applying a force on one surface in one direction and on the other surface in another direction. And I don't want to spend too much time dwelling on twisting and skewing, really. So when we stretch, we say that the object is under tension. When squashing, we say it's compression. When twisting, we say it's torsion. And when skewing, we say it's shearon. It doesn't have the same suffix, don't know why. So we have shear forces cause a skewing effect. Stretching will end up looking like this afterwards. Compression will end up looking like this afterwards. Torsion will end up, well, how on earth am I going to represent that on 2D? I'm going to struggle. But shear would end up looking like this. It's kind of one side has been sheared and the other side has been sheared in the other direction. Something like that. Torsion is a really difficult one to draw, but you know what twisting looks like. So we can have forces of tension, tensile forces, forces of compression, so they're compressive forces, torsional forces, I guess, and shear forces. And we are going to be interested in these two for our A-level physics. The graph that we had for Hooke's law looked a bit like this, but we only showed the first quadrant. We had force and we had extension, but I'm just going to call it delta L, a change in length rather than extension, because our graph went to there. But actually it can carry on. So we'll have our extension over here, and we'll have our compression over there. Just like that. But it's still a straight line, so Hooke's law still applies in both directions. That's just an important thing to bear in mind. Right, now we're going to have a look at different materials. So different materials. We've looked at some different ways of deforming solids. Now let's look at different materials. Different materials. And because I've been drawing force versus extension, or now we're calling it force versus change in length, I'll stick with that convention. I'm only going to be interested in the first quadrant of the graph for now. We can add more later if we want, but there's not much point at the moment. So force, and then I'm going to put change in length. of the object. Now, for a spring, we've already seen what that looks like. That is directly proportional, so it would be a straight line through the origin. That is our spring. In fact, I'm going to do it with a lower gradient, which means less stiff, a lower spring constant, less stiff, just so it's out of the way. Now, we have another elastic substance called rubber. And when you extend that, it does something like that. So that would be something like rubber, but that's still elastic. Whereas we've got some things that do something very interesting, where you can apply a lot of force and get very little extension, and then brum, and then it'll suddenly do that. And that might be something like polythene, where it's quite strong. There's not a lot of extension at the beginning, but then it weakens and it stretches out. Now, the thing about polythene is it gets deformed plastically, whereas the rubber gets deformed elastically. So I'll say rubber deformed elastically, and we can say that the polythene gets deformed plastically. Sometimes it's called inelastically. So what does that mean? Well, elastic deformation means that when forces are removed, it will return to original shape. Whereas the plastic deformation is it won't. So with plastic deformation, we have permanent deformation. It's permanent. We remove the forces, but it doesn't return to its original shape. And you've probably all seen this with a rubber band. You stretch it, you release it, and it goes back to its original shape. But a plastic carrier bag, you put your shopping in it, you get back home, and all the handles are stretched. They don't go back to the original shape. They're stretched permanently. Now, you'll get some elastic deformation down here for polythene, but then you end up with plastic deformation over there. So these are the sorts of things you'd expect to see. Metals are very interesting. So this is force versus change in length. But actually, that's not really good enough, is it? The problem with talking about force and different lengths is that I could have a longer piece of rubber to start with. And if I've got a longer piece of rubber to start with, then for the same force, I'm going to get more change in length. Or I could have a thicker piece of rubber to start with, a bigger diameter. And then for the same force, I get less change in length. So this diagram is for a particular piece of rubber of a particular geometry, or a particular geometry of spring, or a particular geometry of polythene. In other words, these graphs are geometry dependent. And that's not really ideal. When we talk about materials, we're talking about selecting the right material for the right application, and we don't want to have to look up the geometry of the material as well to make a judgment about which material to use. That's just, imagine the catalogue for every single possible size and shape of steel just to know whether steel is the material you want to use. I need it to be certain strength. Right, okay, I need it to have the certain extension under the certain force. Right, well, that depends on the actual geometry we started with. So let's get the big book of steel girders out and have a look what different lengths and different diameters do and so on. That's not reasonable. So what we need is quantities to replace force and replace the change in length, which are independent of geometry. And that leads us on to stress and strain, particularly tensile. We'll talk about stretching, so we'll talk about tensile stress and tensile strain. We could be talking about compressive stress and compressive strain. It wouldn't be any different. Although with strain we'll talk about extension, and it would be a compression rather than an extension. But we'll just leave it like that. So tensile stress and tensile strain. What we want to do is replace each of these force and change in length with something that makes it geometry independent. So let's start with the change in length. Now, we already know from last lesson that if I double the length of a piece of material, it is as though I placed two of them in series, and that has the effect of halving the spring constant and thus doubling the extension that I get for a given force. So if I double the original length, let's make a note of this. Consider, we're starting with strain here, so consider original length of a wire, and I'm just going to draw that like this, and it's a certain length which I'm just going to call L. Where's my straight line tool? There it is. Straight line tool. And let's call that L. Just like that. I'm going to say consider the original length of the wire L for a given force F. I get extension equal to, let's just write extension delta L equal to F divided by L. Fine, that is true. Sorry, F divided by K. That is true. That's what I get. Now, if wire started twice, spelled twice right, twice as long, and now I'm going to try and do my best to draw it. Oh, I've left it to the end of the line. That'll be okay. I'll draw it underneath. Twice as long, just like that. Let's get out my straight line tool, change it to orange, just like that. Straight line tool. Now the pencil stopped working. There we go. And this is now 2L, so it's now started twice as long. For same force, we get 2 delta L, right? We have to get that because K will halve. So K depends on the geometry, as we can clearly see. So we need a quantity that related to the material that doesn't depend on geometry. But in order to figure that out, we need a substitute for the extension. We're going to get twice the extension if we start with twice the original length. So we use strain instead. So we use tensile strain instead. So the tensile strain is going to be using the symbol epsilon, which is that Greek letter there, is going to be the extension. And that's only because it's tensile, we say it's extension, divided by the original length, which we could call natural length. Original length. Sometimes we call that natural length. That is what strain is. In other words, it is the delta L divided by the L. Now we've divided by L. We've divided by that original length. We know that if I have double the original length, I end up with double the extension. 3 times the original length gives me 3 times the extension, 5 times, and so on. So this quantity, it doesn't matter what the original length is, it gives me the relative extension. That's what it tells me. So I can replace in my graph extension with my strain, my tensile strain, and now all of a sudden I don't care what the original length of that material was. Now we could do the same thing for cross-sectional area. Area. I do hope you're following all this. So if we go back to last lesson's notes, you remember we said, well, if I cut this shape in half, it's like having 2 shapes next to each other. They get the sum of these 2 forces is equal to this, and we figured out that actually that is no different to looking at springs in parallel. And with springs in parallel, what happens? Well, the spring constant is higher, it's stiffer. So the more of these we stack up next to each other, the wider the spring, the wider the piece of material, the greater the cross-sectional area of the material, and therefore the stiffer the spring. So we need to get rid of the dependence of the stiffness upon the cross-sectional area. We've already dealt with the length with strain. If we deal with the area as well, then we've dealt with every coordinate related to the geometry. So instead of force on our graph of force versus change in length, we've already replaced change in length with strain. Instead of force, we use stress. And the logic is the same, so I don't want to go into it again, but we use stress. The stress is the force, the tensile force, if this is tensile stress. So let's say tensile force divided by the cross-sectional area. Now, an interesting point about this is that the cross-sectional area has to have an area vector in the same direction as the tensile force. And what do we mean by area vector? Well, the area vector is perpendicular to the plane of the area. So in other words, if this is the area, that's the area vector A, perpendicular to the plane, and we need that to be parallel to the tensile force T. So the area we choose, the cross-sectional area we choose, is the one where the area vector is parallel to the tensile force. So let's just label that A and then label that T, because that might help remind us in our notes, where T is the tensile force. Or perhaps I should name that F instead of T. Tensile force and tension, by the way, are synonyms. They mean the same thing. F. There we go. So that has to be 90 degrees to that surface. Okay, so now our graph no longer has force and extension. Our graph now has stress and strain. And so let's have a look at what that would look like for a material. And I'm going to do this nice and large here. It's now independent of geometry. We've got stress, and we use the symbol that for that. And we've got strain. And these are tensile stress and tensile strain. Now, we can choose to have strain as our independent variable in the same way as we could choose to in this previous lesson, choose the extension and measure the force that produces that extension. I think I rubbed that diagram out, didn't I? Where we had a spring and a Newton meter attached. And we pulled the Newton meter to a certain extension and measured what the force was. We could do the same thing here for stress and strain. So we pull to a certain proportional increase in length, and that way we don't care what the actual original length was. We're only looking at the proportional side of it. And then for the stress, it looks like I've written stress. There's definitely an R in there. Let's rewrite that. For the stress, we can measure the force and the cross-sectional area to determine what that stress is. So what happens? Well, on our graph, we get a straight line. That's good. But it doesn't stay straight, and it depends on the material. So if I have something like copper, it's going to come up like this, and then it's going to curve like that. And it's going to be quite a gradual curve. So this is copper. And that's fine, that's what copper does. If we have something like glass, it might be much more stiff. In other words, you're going to have a much greater stress with much less strain, but then it will just suddenly fracture. It's quite brittle. So this is glass. But something like steel, and I think steel is in between these two. The notes say that glass is less stiff than steel. Glass might be less stiff than steel, I don't know. But I'm going to put steel in between these two. Why would I assume that I know more than the notes do? Let's not. Let's do exactly what it says. And then sudden fracture, and that's glass. So it's brittle because we don't get very much strain, and there's not a lot of deformation that's permanent. There's not a lot of permanent deformation with glass. It's only able to be deformed elastically. But if I take steel, steel is very interesting indeed. It starts with a nice straight line like this, then it curves, and it actually curves twice like that. Now, if you're interested in metallurgy, you can study this and work out what's going on with steel. We have some interesting points on this graph. We've got a point here, which I can label P, and that is the limit of proportionality. In other words, it's the point where the graph stops being straight. Proportionality. And all graphs that have straight parts that go curved have limits of proportionality. It's the maximum strain that gives you a straight line. But that isn't actually the point where the material stops being elastic. For steel, the elastic limit is actually just a little bit beyond. So we end up with, come on, draw the E. Has my pen run out of batteries? It might well have done. I repaired the pen and it works, but sometimes things happen. Right, E. So you've got E. E is the elastic limit. So what that means is that if we extend it beyond the elastic limit, it will not return to its original shape. And you'll notice that that's past the straight part. We then have this point here, which we're going to label Y1, which is the first yield point. In other words, the material gets weaker at this point. There's a temporary weakening of the material. The material becomes weaker, and that's why all of a sudden we get less stress as we continue to increase the strain. Remember, in this experiment, strain is our independent variable. So we're pulling away on this piece of steel, and we notice that the stress actually drops. There's a reduction in strength. And we end up with a point all the way down here, which we can call yield point 2, where another thing happens, And I don't want to go into exactly what happens here. It's all to do with crystal grains moving around, sliding past each other, and so on, which you'll study at university if you're interested. And this is another weakening, but it's a different sort of weakening where we go into plastic flow. And then we end up with plastic flow. Let's make it a grey colour. In other words, the material, it essentially flows as it stretches, getting longer and longer and longer. Now we have a point up here at the very top called, well, I'm going to label UTS, just like that. Now the UTS is the ultimate tensile stress, also known as the strength. So UTS is ultimate tensile stress, but that is also known as the strength. That is the maximum stress above which the steel will fracture. You cannot get the stress higher than that. You just can't. And then last point on this, at the very end, is the point where it breaks, which we can just call the breaking point. So that is what steel does. Copper doesn't have quite the same behavior. We get this ductility, this plastic flow, which is ductility, so it's ductile. As we stretch it out, we get that with copper, but we don't get this momentary sort of strengthening there at the second yield point, where it gets a little bit stronger. I think that's all I really need to say about materials. So these graphs are independent of geometry. This is the important point. I can now say for different materials, I know how the stress behaves with strain, or vice versa. So I can now say, well, if I need a material that behaves in a certain way under certain circumstances, I can now look in a table of different materials and then figure out what I need the geometry to do later. So the other interesting quantity here, we last lesson learnt about the spring constant. Yes, for lots of different combinations of springs, but the nice easy spring constant, F equals K delta L, K being the spring constant, the ratio of the force to the extension. Well, now we've got this geometry independent relationship, stress versus strain, and we can use the straight part of this graph right near the beginning to define a new quantity, which is called Young's modulus. It is the gradient of that straight part. Just check I spelled modulus right. Yep. Young's modulus. It's the gradient of the straight part. Gradient. And it is equal to the stress versus strain. It is the change in the y-axis divided by the change in the x-axis. So it's stress divided by strain. And that's it. We probably wouldn't write it with the deltas. We'd probably just write stress divided by strain, because it passes through, the relationship is directly proportional, so the lines pass straight through the origin. So stress divided by strain, specifically tensile stress divided by tensile strain, is the Young's modulus. That's just the geometry independent quantity that tells us how stiff the material is. That's all it is. And so Young's modulus, together with the ultimate tensile stress and any yield points, and even knowing the elastic limit, all of that information for different materials is all we need to be able to decide what material is suitable for what application.